morning, everyone. Everyone's having fun, I guess. May I ask, raise a hand who is not NAG today in the audience? Oh, good. Right. So I just want to know. I want to know what kind of presentation I need to make and how to adopt the content. Thank you. Yes. So I was going to say about operator overloading and code transformation performance a lot today. But I guess the speaker from the previous talk already kind of covered that. He did explain a lot of problems and how difficult that is. We at MatLogica realized that, and we worked on this problem for a number of years. So today is going to be a little bit different. I'm not going to go into too much technical detail, but maybe I'm going to go and tell you a story about MatLogica and the results we achieve. Right. Is it not working? This way. OK, so it all started in 2018. This is when MatLogica was born. I was joined myself with my colleague, Evgeny. And we worked on the first prototype. And the first prototype is probably something along the line of presented earlier CodeGen technology. And it's available on GitHub, free of charge. You can download it there. It's been there for 2 years. And the prototype was very interesting to play with. We did use operator overloading to generate code for forward and for joint. So what were key results of that initial R&D we did? It has great potential, great performance. We can apply vectorization automatically, because we know that in most cases people want periodic calculations, such as Monte Carlo, but not limited to Monte Carlo. But it needs custom JIT compiler to be successful in practice. And this is a very crucial part. It's impossible to use a compiler off the shelf to make this idea work, because compiling a very long program, forward and adjoint, takes time. And this time is something we want to save. So if compilation consumes longer than computing all the sensitivities, then the whole idea just doesn't fly. So in 2018, we've spent this year developing something that we can call MVP. So something that can be used in practice and something that works fast. We knew it's going to be a tough life ahead of us. So we did file a patent to cover this technology. And the idea here is to gain some ground on the market, just so some serious players who have already established connections with big players in the market will consider us more seriously and will give us a chance to deliver the technology we believe in. The first publication about this approach was in the same year, shortly after patent submission. And we did specifically talk about breaking the primal barrier. Although, yes, it really depends how you define primal and whether or not it's possible to break it. We still think we achieved tremendous results. We were able to calculate primal values and sensitivities faster than original code. In practice, you do deal with real-life situations. You don't always deal with code that is highly optimized already, that is multi-thread enabled from the beginning, and something that doesn't allow any further optimizations. And previous tools couldn't help users to extract more performance from their existing code bases. And with this approach, with the approach of extracting violation graph and compiling into machine code on the fly, we were able to optimize original code and, in the end, achieve speed-ups faster than the primal. Specifically, we say in this article, Our innovative idea is to cross both approaches, namely use operator overloading to integrate AAD and generate code for the Primal function and AD version of the Primal function at runtime. Yeah, that was in 2019. This is when we started to work on this idea. Getting out there, so we presented this idea at a number of conferences. WBS, QuantMinds, back in the days when real-life events were possible. Thanks to these QuantMinds organizers as well, we can do it here. We also presented these results at scientific conferences, including AAD conference, where we were faced with interesting responses. But people generally liked it, I guess. So facing the real world, I mean, it's one thing to have something theoretical. It's another thing to capture not a preview, not something that works in a very limited scope. We wanted to get something that works for real applications, something that our potential customers want to do. We did joint work with Intel, and this was a very interesting collaboration. So we saw the results that can be achieved with vectorizations. We demonstrated that jointly with Intel, how AVX2 and AVX512 vectorizations can be used to accelerate primal and adjoint codes, in this case specifically for Monte Carlo. You may hear that running XVA simulations and implementing AAD for that could be a difficult problem, and a difficult problem to achieve decent adjoint factors, adjoint performance factors. We were able to do so. In this example, we were running 30,000 interstate swaps, each maturing in 20 years. And we were running like 64,000 Monte Carlo simulations. We observed similar primal performance results, similar to smaller portfolios. So we saw little or no degradation in AAD performance due to problem size. So if you have a question, you can ask questions, but we also ask a lot of questions our clients, and we did get a lot of them. To some of them, we did not know answers in the beginning, and it gave us a lot of opportunity to grow and extend our technology to answer these questions. This is the early feedback we received from technology professionals. One of them is Robin Hogan. He's author of Adept C++ library. I think Adept C++ library is of good quality. It's open source library based on traditional operator overloading technique to record all the adjoints, local adjoints on the tape and interpret them backwards. And we did a lot of benchmarking of our technology with Adept. I mean, the previous slides that you saw were about 20 times faster than Adept implementation for this XVA problem. But still, there was a lot of work ahead of us. We needed to prove that this technology can work in practice. So, and in many places, you have to deal with quant libraries of very large sizes. And thankfully, we have an open source project, QuantLib. And we were able to test our integration approach and integrate with the quant library. With the current technique established, I would probably be able to do this integration in a matter of a day or so. I'm not conservative here. You probably saw from previous speaker that QuantLib code isn't very efficiently written, right? So yes, it's possible to extract more performance from QuantLib using operator overloading code generation tool. And the reason for this, because this technique allows to optimize calculations and focus on what's important. What we also know from experience that we can actually get a lot more performance from QuantLib using our tool. And there are a multitude of reasons for that. I'm not going to go into too much technical details and some proprietary stuff, but we're able to apply a lot more optimizations, and we're able to generate more optimal code targeting Intel and AMD X2 and X512 code gen. Right, I'm going to do a little demo here while we're presenting, if it works. So let me see. So this is ORE, Open Risk Engine, built on top of QuantLib. And I'm going to run XVA modeling for example 3 from their manual. This is original code as it is. Just trust me on that. And what we do here, we price 5 positions over 83 time steps, and we want to do 10,000 simulations. OK, let's keep it running, and I'll come back to it later.
5 positions, how many parties?
10,000.
And what are the conditions?
It's swaps, swaptions, more swaps, more swaptions. It's not finished yet. No, no. Yeah, I know it's 8% now. Still keep going. Yeah. 5 positions. Yeah, I know it's 5 positions. It's XVA. So you need to price your portfolio across 83 time steps. So 5 position times 83 times 10,000. Right. So it is in QuantLib. Yeah. Underneath, it's a QuantLib. So yeah. It does look ridiculously slow, I admit, yes, yeah. Right, so, sorry, yeah. So fast forward to 2001, I think we right now in a very mature state. Our product is ready for the market. It's not a toy. It's capable of handling very large simulations. And myself, having XVA background, I know how important that is. We're able to price a huge portfolio of swaps. And the benchmark we did with Intel, actually, it's available on GitHub. It's open source. And you can easily play with that, scaling it up and down, and defining how many time steps you want, how many Monte Carlo simulations you like, and how big of the portfolio you want. So just to observe how well your performance scales with the number of CPU threads, for example, etc. Anyway, so I know you probably wanted to know more technical stuff today, and I'm going to do a little bit of that. But if I go into answering all the questions people tend to ask me, I'm going to bore you very much, to be honest. But we do have answers to most of the questions I showed previously. We did a lot of benchmarks this year. We demonstrated how AAD can be applied to price optionality with Long-Schwarz, or to price XVA with Long-Schwarz method. We did test how our technology can be applied for machine learning training. And as you know, backpropagation is basically a subset of adjoint differentiation. And normally, backpropagation is something that is optimized for machine learning. So people tend to go and use tools specialized for that. What we found that our product, AADC, is flexible enough, and at the same time, it's fast enough to be used as a machine learning training tool within your quant library. So you don't need to cross the boundary from your C++ quantum analytics to Python world, train your models there and bring it back. You can do everything within your C++ world. And this is very powerful because I think machine learning concepts can be useful in practice. But like transitioning to a different environment is something that is painful. And with this and operator overloading technique as a way to capture violation graph, the whole concept of building neural networks becomes very flexible and allows you to mix your business analytics C++ code with machine learning concepts such as fully connected layers, all the basic stuff. We also know how to do solvers and minimizers. Yeah, this is a very interesting subject, how to do it automatically. And we can do it for code generation too. Needless to say, checkpointing, we did that from the very beginning. We now have real-life clients, and we prove that by providing them with quick integrations, great performance results, and simplified code base. And where the simplification for the code base is coming from? Many people are targeting performance and flexibility at the same time. So it's very popular to use domain-specific language to capture custom payoffs that can be modified basically on a live trading system. With code generation, you can have best of both worlds. You can have your flexibility of setting up your payoffs in a scripting fashion at runtime, and at the same time converting that into a very highly efficient machine code, right? And it's not new. This approach has been done in the past. I mean, people did convert their scripting language on the fly into something that can be consumed by off-the-shelf compiler, such as your standard C++ compiler. But with AADC, you obviously can also generate adjoints, and it's very fast. You don't need to have this pain of running external compiler on your production system. Right, so back to AAD and how to actually integrate that. This was our story, but what is the useful from this presentation? AAD strategy. Oh, demo, yes, sorry, demo. Right, so it's finally done. It took 377 seconds to run this XVA pricing. And I'm going to run the same thing, but with the ADC enabled version of array in QuantLib. So we still spend a lot of time on reading data from XMLs, etc. And what's happening here, instead of running original code for 10,000 Monte Carlo simulations, we run it for one single Monte Carlo path, and we create machine code to replicate calculations at runtime. In this particular situation, we're not dealing with AAD aspect. We're actually only looking for accelerating our forward calculations, forward pricing. You can see here we have some statistics, like how long it took to compile, and it was 1.3 seconds. We've spent random numbers generation in 0.7 seconds. And we used, in this case, we used 5 threads to run the full simulation. And the evaluation engine completed full XVA simulation for 10,000 simulations in 1 second. Compare that with 377 of the original. Yes, I admit that it's not a fair comparison to QuantLib. Like, QuantLib is a real project, and it was developed and contributed by many people. It's highly object-oriented, with lots of abstractions. And I'm sure you guys don't have that in practice. I'm sure you guys, all the production code is perfectly optimized and multi-thread safe. But it's probably not the case. You probably do have a lot of abstractions, and you do want to have these abstractions because it's flexible for you to develop new functionality. And at the same time, your real quant library, it may or may not be thread-enabled. If it is thread-enabled, you are very good programmers. Right? If it's not, you're probably not taking advantage of the potential that the new CPUs are bringing to the table. Right? So in this case, we did run using 5 threads, but you can run it with more. Right, so what is the AAD strategy? How do you actually integrate AAD into your quant library and get top performance? Okay, a little bit of advertising. Get in touch with us, and we can demonstrate how it works. Yeah, sorry about that. But what is the recipe to achieve fairly straightforward approach to real-life quant library integration? We use a new kind of active variable. It's called I-double, and I stands for in place. And what it means, you can actually use I-double as a replacement for your normal double. It behaves as a normal double. And if you simply do search and replace double to I-double throughout your code base, how big it could be, and recompile and run tests, most likely you get your code running same way as it was. It's going to run a little bit slower, in some cases significantly slower, but it's going to produce you correct answers. That's what's important, right? So this step is like fairly straightforward and can be accomplished very quickly. But what it gives you opportunity to actually start recording machine code at runtime for specific sections of your code. We call it kernels, ADC kernels. The reason for this is like people familiar with CUDA kernels. So what we do here is something similar. We convert valuation graph into machine code optimized for a particular platform. So if you have AVX2 available, we can generate code for AVX2. If you have AVX 512 available, we can generate for AVX 512. And in our experience, we can take more advantage from AVX 512 instructions than off-the-shelf compilers can do. Right? So the compilers should still catch up with this vectorization game. And we work very low level, so we know what's going on there, and we're actually ahead of them. So when you have a recording for the kernel, you can go ahead and run it in parallel, taking full advantage of vectorization and taking full advantage of multi-threading. So your original C++ code base may not be thread safe. I know AD libraries themselves are thread safe, but your client code unlikely thread safe, right? So everything should be thread safe to exploit multi-threading. With this, you keep your original code running in single-threaded mode, very predictable, so no surprises there. And the kernels, they are by definition thread safe. So the whole code is limited. Yeah, and you can get AD risk and faster pricing from it. Right, so in the past year, we worked on multiple examples, how this technology can be applied for. These examples are available for our clients with the source code, and we're happy to share with you. You also can go ahead online and play with ASDC from your browser. I know how painful it could be to download C++ libraries, configuring them, and installing them. Needless to say, some organizations forbid to download anything off the internet. You can go ahead and play with our development server online. So this is a Visual Studio Code running on our server, but accessible to you via browser. So you can even step through the code, look for various examples, and read the manual. Right. This is our team at QuantMinds. So if you're interested, get in touch, and would be very interesting to talk to you about various applications. And perhaps you have more questions for us. Thank you. Sure.
I have a question. Maybe I missed it at the very beginning. So you're saying this approach is kind of in between operator overloading and source code transformation, right?
Yes. Yeah.
And do I understand right? Are you when you inject your machinery or your methodologies, so you would first take one step on the original model,
Correct.
and then create some augmented bytecode?
Yes.
Which is then executed on the fly.
Yes. Yes. So the understanding is correct. You execute your original code for one data sample, and during this execution, you get values for this sample alone, but also we get to know what your evaluation graph is, right? So you send this data to our compiler, and we, on the fly, in streaming mode, convert into machine code. And streaming mode is very important here. We don't want to preserve full evaluation graph in memory, because it's going to be prohibitive, let alone any off-the-shelf compilers wouldn't be able to cope with that. But even just keeping all the sequence of operations in memory is prohibitive, right? We don't do that. So while your code is running for this first data sample, at the same time, in parallel, we start to put together binary code to replicate your calculations. And once it's done, the kernel is capable of running it forward, and it's capable of running it backwards for adjoints. So you can execute your Monte Carlo simulations as many times as you like, or be more clever about it and orchestrate something like Longstar-Schwartz pricing method, where you have sections of in your workflow, like first Monte Carlo, you do that to obtain data needed for regression. You stop, you do regression. You stop, obtain the weights for your basis functions, and do the second Monte Carlo. So all this is possible to orchestrate with that, and each of these steps for Monte Carlo would require for you to record this little kernel for one path, declaring explicitly what inputs and what outputs are. Yeah.
May I ask a follow-up question?
Yeah, sure.
So essentially you have two steps where the AAD comes into play. The first step is where you declare your I doubles, and then you compile using your standard GCC compiler or whatever.
No. Oh, yes, that's completely correct. You do use your standard compiler for your original code, right? So we don't we don't require you to change your original compiler. So we're not compiling your original code. We're compiling evaluation graph, right? And this is a lot easier, obviously. Myself, I wouldn't be able to implement a C++ compiler in the world. But we were able to implement a very good compiler for the evaluation graph. Yes.
And then you say your library is linked to this original program?
Yes, exactly. So the library itself is a set of header files implementing I double type. This I double type, it's nothing but just simply checks if recording is taking place. And if it is, it calls API on our library. And the library itself maintains the state of the program and maintains a state of the compiler. And it keeps writing machine code as you go. Yeah. And when you say it's between operator overloading and source code transformation, I'm not completely agree with that. We actually do see many cases when we go beyond code transformation. And the reason for this, if you think about how code transformation works, code transformation is very efficient. At least it was the most efficient we saw so far. But it still runs at compile time. And at compile time, you may not know all the information available to you at runtime. And we all know that JIT compilers are there because they can take advantage of information available at runtime. So doing this kind of code transformation, how we do it, at runtime can take advantage of this information and can beat code transformation done at compile time. Yeah. Anything else? That's it? Right?
Great. Thank you very much.
Yeah.